Good evening. Today's quote is dreaming after all is a form of planning. Dreaming after all is a form of planning. Today's word is stupendous, causing astonishment or wonder, awesome, marvelous. A person with stupendous wealth. So today's topic is sets and relations. This is fifth topic. Basically, the topic should have been called as sets, relations, and functions, but the functions is altogether different topic. I think topic number six. So sets and relations, you have already done sets, may not be relations, but sets in ninth and 10th standard. So how a set is defined? A set is defined as a collection of well-defined objects. That is very important. A collection of well-defined objects. Okay. You know that sets are usually denoted by capital letters like A, B, C, etc. Okay. Objects that form a set, objects which form a set are called as elements of the set, which are usually denoted by small letters like A, B, C, etc. If an object, say X, is a member of a set A, then we write this as X belongs to A. This is a Greek alphabet, epsilon, EPSILON, which stands for belongs to. So we say that X belongs to A, means X is an element or an object of that set. It is likely that the element is not member of that set. Suppose Y is not the member of that set. We say that Y does not belong to the set A. I hope this is clear to you. Now, representation of a set. This is very important. Actually, there are three methods of representation of a set. The first method is called as roster method, which is also called as tabular form. I repeat, in fact, I will write this. This is roster method, or it is also called as tabular form. Okay, so in this method the elements of the set are actually listed and enclosed within curly bracket. See, this convention is important. Strictly you have to use curly bracket, because if you use circular bracket, then it means that order is important. In set you have to remember two things: order is immaterial and one element is to be written once only. These two rules are to be followed. So 1, 2, 3, 4. Okay. So this is set A. Set B, I can say Monday, Tuesday, and so on up to say Sunday. I may also say that C is 1, 3, 5, 7, dot, dot, dot. Okay. Yes. So this is called as roster method or tabular form. The second one is called as rule method. We state the elements by rule, which is also called as set builder form. Set builder form. Okay. So if all elements of a set A satisfy some property, we say that rather that representation is called as set builder form. For example, consider set A. How can we write that set A using rule method? Can I say that A is set of all X such that, slash means you have to read this as such that X is a natural number. X is a natural number and X is less than or equal to 4, or you may say that X is less than 5. And what does capital N stand for? N stands for set of natural numbers. See, you should know that capital N, set of all natural numbers, we are going to call it as an infinite set. You should be knowing that 1, 2, 3, 4, etc. Now, if 0 is included, it is called as set of whole numbers. I will not write this. W is set of whole numbers 0, 1, 2, 3 up to infinity. It is an infinite set. Then capital I or capital Z is called as set of integers. I hope you know this particular set. It is -2, -1, 0, 1, 2, dot dot dot. Okay, so this is set of integers. Then set of rational numbers, which is represented by Q. How will you define this set? I can say it is P upon Q such that P and Q, they belong to set of integers. But another important condition, Q not equal to 0. Q, if denominator vanishes, it is not a real number. Okay. And finally, R set of all real numbers. Actually, you will say, sir, this is not final, this is semi-final, because finally set of complex numbers. Yes, I agree. But we are basically interested in real numbers. In calculus, we consider functions which are real valued functions. That is why I'm saying set of capital R, set of all real numbers. But it is true that every real number is a complex number. So complex number we are going to call as the universal set when we will discuss the concept of universal set. Okay. Now, how will you describe set C? I'll show you that. Yes, set of all x such that x belongs to n and x is an odd number. See, -1 is also an odd number, right? So don't say only odd number. Say it is a natural number, but it is an odd one. How will you describe set B? B set of all x such that x is a day in a week. So this is how we can represent the set using second method, which is called as a rule method or set builder form. Now, which is the third method? Actually, credit should be given to these two gentlemen. Uh, when some pronounce this as Euler, some pronounce this as Euler. So when Euler diagram, a set can be represented by a closed geometrical figure like a circle, a triangle, a rectangle, etc. In fact, in some cases, you can use this amoeba because it is a closed figure to represent a set, but usually circle is used to represent a set. So such a diagrammatic representation of a set is called as Venn diagram. The points inside the figure represent members of the set. Okay. Um, you are aware that generally we use this rectangle to represent the universal set. You must have done this in probability. Okay. So suppose elements are 1, 1, 2, 4, etc. So these are the elements of the set A. Now, number of elements of a set. Suppose S is a finite set. What do you mean by finite set? That number is countable, number is limited, it is not infinite. So if S is a finite set, then the number of elements in the set S is denoted by what? It is denoted by n of S. Suppose set A is 1, 2, 3, 4. Can you tell me what is n of A? N of A is nothing but 4. I hope you had done this in probability. In that case, use the word sample space. So n of S, set of, rather number of sample points in the sample space. Okay. Empty set, empty, which is null set, which is denoted by phi. This is another Greek alphabet. So the empty set phi does not contain any element. So it is n of phi. N of phi is nothing but 0. Some students think that this is an empty set. No, we are going to call this as singleton set. Yes, this is an empty set. Okay. Yes. So This is about number of elements. Actually, it is also called as cardinal number, or n of s is also called cardinality of the set S. Now we discuss different types of sets. The first one is empty set. A set which does not contain any element is called the empty set, null set. One more name is there. It is void set, VOID, void set. The empty set is usually denoted by phi or using this symbol. Okay. Now, can you give me examples of null set or empty set? Yes, very good. So the example of empty set is, I can say that set of all real numbers whose square is negative, right? There is not a single real number whose square is negative. So that is example of empty set or null set. Second is singleton set, a set having only one element. Remember, phi is what? Null set or empty set. But if I write like this, is this an empty set? No, it is a singleton set because this contains only one element. I can say that set of all real numbers which are neither negative nor positive. Yes, that is 0. So this is singleton set. Set of all present prime ministers of India or presidents of India, or set of all present chief ministers of India, only one. So it is singleton set. Then comes finite set and infinite set. A set containing a finite number of elements is called a finite set. Thus, in a finite set, one can count number of elements or actual elements. For example, set of all days in a week, or set of all alphabets, English alphabets, set of all consonants in English alphabets, etc. Or set of all students in a class. All these are examples of finite set. A set which is not finite will be called as infinite set. Now there are many examples: set of natural numbers, set of integers, set of rational numbers, then set of real numbers. All these are examples of infinite sets. Then comes the concept of subset. Now you have to listen to me carefully. If every element of a set A is also an element of set B, then A is said to be a subset of B. We write this as A subset of B. Symbolically, we can write this definition as A subset of B, IFF. See, IFF, you may say that, sir, you have written wrong spelling. No, this is standard short form. It stands for if and only if. If and only if X belongs to A implies. See, we will be discussing this in the topic logic in 12th standard. Implies X belongs to B. Okay. So it is clear from the definition that every set is a subset of itself. I hope you are getting this. Note that phi is subset of every set. Okay. Yes. Now next concept is proper subset. If all elements of set A are in set B, if all elements of the set A are in set B and B contains at least one element which is not in A, we say that A is a proper subset of B. And in this case, we write in this fashion. We say that A is proper subset of B. Okay. For example, if I say A is 1, 2, 4 and B is 0, 1, 2, 4, right? So A is a subset of B, but B is not a subset of A. That is, there exists at least one element in B which is not an element of A. So A is a proper subset of B. Now, this is an interesting point. Suppose Suppose there are 10 elements in a set A. Okay, so n of A is 10. Can you tell me total number of subsets? I repeat the question. In a set A, there are 10 elements. Can you tell me total number of subsets? Type your answer in chat box. So, if in a set, my previous question was 10 elements, how many subsets? Answer 1024. Now I will consider a smaller set, set A, containing 3 elements. Let us list all the subsets. In fact, we are going to call it as power set. What is power set then? The set of all subsets of a given set, say A, is called the power set of A, and it is denoted by what? P of A. So this is basically P of A. Okay. Now set A 1, 2, 3. So empty set is subset of every set. Now I will consider one element at a time. So these 3 singleton sets. I will consider 2 elements at a time. So 1, 2, 2, 3, 1, 3. Now every set is a subset of itself. So in all, how many? 8. So you should know that if in a set number of elements is n, then there are how many? 2 raised to n subsets. And that is why if number of elements is 10, number of subsets is 2 raised to 10. That is 1024. Is that clear? So can I say this is nothing but n of p of a? What does p of a stand for? Power set. Okay. Yes. Now definition of equal sets. Two sets A and B are said to be equal if they contain the same elements. That is, A is subset of B and at the same time B is subset of A. We say that A equal to B. Yes. Now equivalent sets. See, this definition is important. Equivalent sets. Two finite sets A and B are said to be equivalent if n of A, equal to n of B. See, I am not saying equal sets. It is true that if two sets are equal, then they are equivalent also. But equivalent sets need not be equal sets. I'll give you an example. So set A is 1 to 4, set B ABC. What is n of A? 3. What is n of B? 3. So they are equivalent sets, right? But are they equal? They will be equal. They can be equal if A is 1, B is 2, C is 4. Or B is 1, A is 2, C is 4. Right? Or if I consider set C as 6, 7, 11, then A and C are equivalent sets, but they can never be equal sets. Okay. Now, the next important concept is universal set. How will you define universal set? Please unmute and tell me the answer. My next question is, can this be a universal set? Is it possible that such a small set is universal set? Basically, how universal set is defined? A set, say X or omega, is said to be universal set if all the sets under consideration are subsets of that set. Universal set, as I said, is denoted by capital X or universal, so capital U, or by omega. See, if I say that set A contains 1, set B contains 2, can I say that A and B are subsets of this set? Yes. So any non-empty set of which all the sets under consideration are subsets is nothing but universal set. In Venn diagram, how to represent universal set? It is represented by rectangle. So this is U This is set A and this is set B. This is set A, this is set B. Okay. So I repeat the definition. Any non-empty set of which all the sets under consideration are subsets is nothing but universal set. Is that clear? For example, set of all colleges in Asia is the universal set, for which sets set of all colleges in India, then set of all colleges in Maharashtra, set of all colleges in Pune, set of all colleges in Kothurud, Pune, right? So set of all colleges in Asia is the superset for the other sets. So it can be considered as universal set. Now, few more things, then we'll start solving sums. Actually, this part is very important. Operations on sets. Let me explain that. The first one is complement of a set. Complement. Complement of a set. Let A be the set which is the subset of the universal set, say U. Then the set of all those elements of U which do not belong to A is called complement of A with respect to U, and it is denoted either by A dash or A bar. Actually, there is one more notation. A complement, AC. Okay. So how A dash is defined? A dash is defined as set of all x such that x belongs to U, but x does not belong to set A. This is the definition of complement. What will be the complement of the complement? Original set. Suppose we'll consider a particular example. Suppose U 1, 2, 3, 4, 5. A 2, 4, 5. So what will be A dash? What will be A dash? A dash will be elements which are in U but not in A. So I have to include 1. I cannot include 2. I have to include 3. That's it. Right? Suppose set B is 4, 5, 6. Who will tell me B complement? Type your answer in chat box. Now when you type, you need not use bracket, just write elements. I repeat the question. B is 4, 5, 6. Can you tell me B dash? The correct answer is, see, when I say that U is the universal set, right? So the element 6 is not part of that set. So how can we find complement of B with respect to U? It is not possible. Okay. So your answer should have been no, no, no. We cannot find B complement because B is not a subset of so-called universal set here. Okay. Now what are the properties of complement? There are many properties. I can list few of them. That complement of complement is original set. Then what is complement of universal set? Null set. So what is the complement of null set? Universal set. Okay. So there are actually two more, but we haven't discussed that. That A union. We haven't discussed union yet, but A union A dash is nothing but universal set. Then A intersection A dash. We haven't discussed intersection yet, but still intersection means common elements. Not a single element is in common. So it is null set. Okay. Now diagrammatic representation of A dash. So this is universal set. This is set A. So this is A dash. This is A dash. Now I will tell you importance of considering complement of the event. Basically, we will be using this in probability. Suppose The sum goes like this. A problem in mathematics is given to 3 students. And suppose they are solving that problem independently. This is purely hypothetical case, because usually when the problem is given, students, they start discussing, but everybody is at his or her home right now. So we can assume that students are solving problem independently. And if probability of the event, that problem is solved, is asked. I repeat the question. A problem is given to 3 students, say ABC. What is the chance that problem is solved? If you consider original event, that problem is solved, you have to consider number of cases. Okay, which only A can solve the problem, only B can solve the problem, only C can solve the problem, still problem is solved. A and B solve the problem, A and C solve the problem, B and C solve the problem, and one more case, seventh, all of them could solve the problem. Now, instead of considering these 7 cases, if we consider its complement, what is the complement of problem is solved? It is problem is not solved. Only one case. A cannot, that is A dash, and means intersection. B cannot and C cannot. Right? So in such cases, it is better to consider the complement of the original event. Then comes union of 2 events. This definition is important. If A and B are 2 sets, then the set of those elements which belong to A or to B or to both A and B. This is important. Some students think that the elements which are in common are not to be taken into consideration. No, you have to take every point, but remember, one point is to be considered once only. Okay. Now union is denoted by this symbol U. So A union B. How will you define that? I will not consider example because it is simple one. All X such that X belongs to A or oblique and X belongs to B. Okay. This is A union B. Now, how to represent? There are actually 2 possibilities. In fact, there are 3, but I'll just show you one possibility. So this is A union B. This is set A. This is set B. Okay. So this is about union. What about intersection of sets? How will you define that? Common elements. A intersection B, set of all X such that X belongs to A and sorry, and oh, X belongs to B. Okay, so this is nothing but intersection of sets. Now that intersection can be empty also, empty set also. So this is A, this is B, this is universal set. Yes, this is what? This is A intersection B. Now if A intersection B is 5, then it is, then the sets A and B are called as disjoint sets. Why? Because not a single element is in common. Suppose set A is set of all boys in a class, B is set of all girls in a class, then A intersection B is a null set, void set, empty set. Okay. Now, in that case, Venn diagram will be like this. So this is representation of disjoint sets. Okay. Then there are many properties of union and intersection. Uh, I don't think I'll be able to upload that file today, but definitely by tomorrow evening, I'll be uploading a theory file. Today, I'm going to upload homework file. There are 2, 3 exercises in that homework sheet. Okay. So this is about operations. There are actually many operations, but we will not discuss all the operations right now. We will solve few examples and then we'll discuss the remaining. Exercise 5.1. First question, describe the following sets in roster form. First one, A, all x such that x is a letter of the word movement. Remember, one element or letter, whatever object of a set is to be written once only. So MOVENT. Do not write E twice, M twice. Okay. Second, B, set of all x such that x is an integer lying between -3/2, that is -1.5, and 9/2, that is 4.5. You can draw a number line. So you will realize that -1, 0, 1, 2, 3, 4 are the elements. Do not include 5 because x has to be less than 4.5. Third one, set of C is set of all x such that x is 2n plus 1, where n is natural number. First natural number is 1. So I hope you won't say this is 21 plus 1. This is 2 into 1, 2 plus 1, that is 3. For n equal to 2, 4 plus 1, 5, 7, 9, and so on. This is an infinite set. So that's it for today.